So we're going to take a look at some magnetism today. Before I write on my smartboard with a red pen, how about I stop doing that? Okay, so in this problem, an electron in an electron beam experiences a downward force of some number while traveling in a magnetic field of some other number west. They give us the elementary charge, proton. Proton charge is elementary charge, as is the electron charge. They're just positive and negative. And then the question is, what is the magnitude of the velocity? So in short, we're dealing with a charged particle. In this case, it is an electron, to be precise. So it's an E minus, and it is moving to the west. Let's see. And they want us to determine how fast it's moving to the west. We're trying to find the magnitude of the velocity, the speed. All right, so I'm going to erase the W, but we'll say that this way is west. Up is north, that way is east, this way is south, that way is west. Okay, so of the information that we are given, we are told that it experiences a force from a magnetic field, and we are given it experiences a downward force of 4.0 times 10 to the negative 14 newtons. And we are also told that the magnetic field strength is equal to 4.8 times 10 to the negative 2 Tesla west. So our magnetic field is this way. Oh, no, I'm sorry. I was going to say, it's traveling to the west. I need to read more carefully. I was going to say, we're about to run into some problems. Let's see, it experiences a downward force. Okay, we'll work with that in just a moment. Traveling in the magnetic field of, 4.8 times 10 to the negative 2, and it's traveling to the west. They want to know what the magnitude of the velocity is. All right. We appear to be missing some information, but here's where we remember what we're actually looking at. It is an electron, and so the charge of an electron is technically equal to negative 1.6 times 10 to the negative 19th coulomb. A proton would have the exact same charge except positive. These are universal values for these particles, at least for our purposes. So we end up with the following. We're looking at a magnetic force on a charged particle that is moving through a uniform magnetic field. Let's see. While traveling... Oh, I'm sorry. The magnetic field is to the west. I'm reading this wrong. Because there's a second question that says, what is the direction that the particle is actually moving in? The magnetic field is to the west. Okay? And it experiences a force downward. So we're going to say downward. Well, if this is west, that's north, that's east, that's south, then I'm looking from above. Our force is actually going to be into the board, pushing the charge downward. So keep in mind, we're looking at basically a map, north, east, south, west. And if it experiences a force downward, that's not south, or they would have said south, downward would be towards the ground. We're looking from above, so it would be into the board. All right, here's what we need. The Lorentz force, the magnetic force on a charged particle, is equal to QVB times sine of the angle between them. We're going to assume that the angle here, I think it says perpendicularly, but that's okay. The angle here is actually 90 degrees. Most of the time, that's what it's going to be in class, which means this whole thing goes to simply 1. We have a force of, if I fill in my force, we've got 4.0 times 10 to the negative 14 newtons is equal to our charge, which we said was technically negative. I'm just going to take the magnitude here because we're going to keep track of direction later. But it's 1.60 times 10 to the negative 19th coulombs times our speed, our velocity, although again, I'm kind of ignoring directions here. We're going to deal with that afterwards. And then times the magnetic field, which is, let's see, magnetic field was 4.8 times 10 to the negative 2 Tesla. If I want to solve for v, I got to divide things over to the other side. So here we go. 4.0 times 10 raised to the negative 14 divided by the quantity of 1.6 times 10 raised to the negative 19. Be careful in how you put these into your calculator, or else you might end up with kind of some weird values. Okay, divided by the quantity of 4.8 times 10 raised to the negative 2. All right, so if I've done this correctly, 3, 6, I find that my speed is equal to 5.208 times 10 to the 6 times 10 to the 6th meters per second. Now, that's an extremely large speed. However, these are extremely small particles, and many times we get them going really, really fast. In this case, when I double check my values, the correct answer is 5.20833 times 10 to the meter, or times 10 to the 6th meters per second. This is indeed the correct answer. Great. We've got our force. It's a very small force, but on a very small charge, and it's a relatively, well, actually, that's a pretty strong magnetic field, but that's neither here nor there. So we end up, when we solve for our speed, the speed that it must be going is very, very fast. It's a little above, maybe it's close to 2% the speed of light. We're ignoring relativistic effects. The second part of this question is one that's also an important one. So now we've got an idea of how fast this charge is moving. Now they ask, what direction is it moving in? Well, all right, if it experiences a force to the west, or I'm sorry, not a force to the west, if the magnetic field is to the west, so this is my magnetic field, and the force, we said, was into the board. Here's where we're going to have to work backwards a little bit. I'll remind you that we saw that the force is equal to QV cross B. We talked about this in class where V is going to be our first vector, B is going to be our second vector, and the force is going to be our result. We use the right-hand rule, the second one that we introduced in class, but it's the main right-hand rule. So I would point my fingers in the direction of V, but here's the problem. I don't know which direction V is in. I do know that whichever direction it is, I'm going to have to curl my fingers towards B, so I'm going to have to curl them this way, and I know that my force needs to point into the board. So here's what I'm going to do. I'm going to put my thumb into the board, and then I'm going to see which way I needed to curl my fingers towards. So this is kind of a pain. I'm certain there's an easier way to do this. All right, I'll do this the hard way. My thumb into the board, and I would curl my fingers up towards B to get that done. So theoretically, my velocity should be down, but remember, the right-hand rule applies to positive charges. Negative charges do the exact opposite, which means we think that the velocity should be down, but in reality, the negative charge would do the opposite. It's actually moving up. So for the negative, moving up, then we would have, let's see, I point my fingers in the direction of the velocity, I curl my fingers towards the second vector, the magnetic field, and I would predict that it would have a force up out of the board, off of the map, except since this is a negative, negatives do the exact opposite, it feels a force downward. We're double checking that. But either way you look at it, we find that the first vector, our velocity, should be pointed like this. And remember, our setup was that this is north, east, south, and west. This is a bird's eye view of the map. The force is downward into the map. So upward is out of the page, out of the map. And so we end up with this. My first vector curled towards my second, and it would experience a force upward, which is the opposite of what we have, except it's a negative charge. They do the opposite, so it experiences a force downward. Therefore, my speed, my velocity, is directed up on my drawing, which is to the north. This is the really hard part about magnetism. It's dealing with three-dimensional vectors. So this question is actually much harder than the first question, which is just kind of math. We actually have to kind of predict what's happening.